Improper integrals. Type 1 improper integral is an integral where we have infinity at upper limit, lower limit of the integral, or both limits. If the function f is continuous over a and infinity, the value of the improper integral, if it converges, is equal to the limit of integral a to b f of x dx when b approaches infinity. So it's defined by a limit. If the limit exists, or it's better to say if the limit is finite, then the limit is going to be the value of the improper integral, and we say that improper integral is convergent. If the limit does not exist, the improper integral is called divergent. So in case we have minus infinity to infinity, then we write a in lower limit instead of minus infinity, and we say that a approaches infinity, and we study the same way. But in case we have minus infinity to infinity, we are going to have two limits. Once a approaches to minus infinity, another limit when b approaches infinity, and both limits must be finite, then we can say that the improper integral is convergent. If one of the right-hand side limits in part 3 does not exist, then the improper integral is divergent. We don't need to study the other one. The type 2 improper integral is the case that the limits are finite, a to b, these are finite. F of x is continuous over half open interval a and b. It means that it is not continuous at one of the limits of the integral, at a or b. If it is not continuous at a, then we write integral from c to b instead of a to b, and we say c approaches to a, but it will approach from positive side, since we know that integrating from a to b, x is somewhere between a and b, and if it wants to approach to a, it must approach from right-hand side or from positive side. If the function is discontinuous at upper limit, then we write c here, and we say c approaches to b, but we should know that this is one-sided. So c approaches to b from left-hand side, from a to b, from left to right, or the limit is one-sided limit. And if the function is continuous over a and b, but not at c, which is a point between a and b, not a and b itself, then we need to separate the integral into two parts. Once that c is in lower limit, another time in upper limit. For each of these integrals, we need to write the limit, like part a and b, 1 and 2. And if both limits, in this case, are finite, then left-hand side integral, or this improper integral, has that value, and it is convergent. If one of the limits in right-hand side does not exist, the improper integral is called divergent. So as an example of type 1 improper integral, we can see that this function is continuous from 0 to infinity. But since one of the limits is infinity, to study this, we need to write a limit from 0 instead of upper limit. I write b, and we say that b approaches infinity, 16 tan inverse x divided by 1 plus x squared dx. So since derivative of tan inverse is next to that, so if we consider tan inverse as t, then this is t dt, and integral of t dt is t squared over 2. Or this is the limit when b approaches infinity of 8 times t squared, but t is tan inverse x squared, from 0 to b. And then we write the limit of 8 times tan inverse b, there's a square here, when b approaches infinity, minus, at lower limit, we have 8 times tan inverse 0. So tan inverse 0 is 0, and tan inverse, when b approaches infinity, this is pi over 2. So we have 8 times pi over 2 minus 8 times 0. So it is 8 times pi squared over 4, or 2 pi squared. Since the limit is finite, then the integral or improper integral is convergent. Improper integral is convergent, or we say it converges to 2 pi squared. This time we have minus infinity to infinity. We need to study two integrals. So it's going to be integral from minus infinity to somewhere between minus infinity and infinity. And the usual point that we can write can be 0. You can write any number, but 0, since its substitution, is going to be easier. 2x e to the minus x squared dx plus from 0 to infinity e to the minus x squared dx. Now we find them separately. First one is the limit. This is lower limit, then I write here b to 0 when b approaches minus infinity, and other one is another limit. So these limits cannot cancel out by each other. So we should have two finite values, and their sum is going to be finite. Otherwise, if one of them is infinite, then we don't need to find the other. We can say that the improper integral is divergent from 0 to b. Sorry, it's better to write here a, this is lower limit, and b for upper limit. It doesn't matter, we can write t or any other name, but to show that it was lower limit, I write a, and there b. b approaches positive infinity, 2x e to the minus x squared dx. Now how can I find the integral? It's clear, it's u prime e to the u, and we know that e to the u has derivative u prime e to the u, or integral of u prime e to the u is e to the u. But what's the derivative of minus x squared? It is minus 2x. We just need a negative sign here. So the first integral is minus e to the minus x squared from a to 0. A approaches minus infinity plus minus e to the minus x squared from 0 to b. b approaches infinity. First integral in the upper limit is e to the 0, 1 by that negative sign, minus 1, minus. At lower limit, it's going to be the limit of minus e to the minus a squared when a approaches minus infinity. But when approaches to minus or positive infinity, a squared is going to be positive infinity, and e to the minus infinity approaches 0. So this limit is 0. So this is for the first integral, and the same for the second integral. For the second, at upper limit, we have the limit of minus e to the minus b squared when b approaches positive infinity minus. At lower limit, we have 0. It is minus 1 here. Now we see that this part approaches 0, this one approaches 0, and we have minus 1 plus 1, which is equal to 0. And this is type 2 improper integral, because At upper limit 4, the function is discontinuous, or the limit of this ratio approaches infinity. Now I need to write limit from 0 to c when c approaches 4 from left-hand side, from 0 to 4 from left-hand side. And instead of this root, I can write 4 minus x to the minus 1/2 dx. The limit is here, c approaches 4 from negative side. And this one, if we use substitution for minus x as t, then dx is minus dt. We have a negative sign. And t to the minus half, we need to add 1 to the power, which becomes t to the 1/2 divided by 1/2. So it is minus 4 minus x to the half divided by half, looks like multiplying by 2 from 0 to c. So at upper limit, we need to write a limit, which is minus 2 times 4 minus c, when c approaches 4 from negative side, minus. At lower limit, we have minus 2 times 4 minus 0 to the 1/2. So when c approaches 4, the limit of the first part is 0. And 4 to the 1/2, or root 4, 2 times 2, 4. And we have two negative side, which is plus 4. This one also is convergent. So up to here we had 3 integrals, all convergent. Second type, improper integral, but the point that the function is discontinuous is between 0 and 2. So we need to write two integrals from 0 to the point that the function is discontinuous to 1. And I can write again this one as absolute value of x minus 1 to the minus 1/2 dx plus another integral from 1 to 2, the same absolute value of x minus 1 minus 1/2 dx. So instead of 0 to 2, we wrote the integral 0 to 1, 1 to 2. But we know that when x is between 0 and 1, it is less than 1, then absolute value of x minus 1 is negative. X minus 1 is negative, then absolute value of x minus 1 is 1 minus x. And other one from 1 to 2, but here x between 1 and 2, x minus 1 is positive, then we don't need the absolute value, we just write x minus 1 to the minus half dx. Now we continue by limits, because now we have improper integrals. We need to write limit first from 0 to, I will use a and b to show that these are two different limits. We shouldn't combine them. Then b approaches 1 from left-hand side, 1 minus x minus half dx plus limit from a to 2 when a approaches 1 from right-hand side, because this time it is between 1 and 2, so it will approach the 1 from right-hand side. And this is x minus 1 minus half dx. Now the integrals are the same, just we need to find the limits. So here, 1 minus x, like u to the minus 1/2. So u prime is minus 1. We have another extra negative sign. Minus half plus 1 becomes plus 1/2. Divided by 1/2 is the same as multiplying by 2. So it is minus 2 times 1 minus x to the 1/2, or root this time. From 0 to b, when b approaches 1 left-hand side. And we can see that this root is defined when b approaches to 1 from negative side. And the other one, limit 2 times x minus 1 to the half from a to 2 when a approaches to 1 from positive side. Now let's write the limits separately. First part, at upper limit, I have the limit of minus 2 root 1 minus b when b approaches 1 from negative side. This is upper limit. Minus lower limit is minus 2 times root 1 minus 0. Plus, for the second integral, at upper limit we have 2 root 2 minus 1, and at lower limit we have limit of 2 root a minus 1 when a approaches 1 from positive side. Again, we say that these limits are 0. And the final answer, we have 2 plus 2, which is 4. So this improper integral converges to 4, or it is convergent. Another improper integral from 0 to 1, which is again second kind or second type. However, if I use substitution, we can consider as first type. Let's study directly first, and then I will use substitution to show that we can study as first type improper integral. So you know that ln x when x approaches 0 has infinite limit. So we can write limit from a to 1 when a approaches 0 from positive side minus ln x dx. Integral for ln x, we know that we can use the bypass technique, and integral of ln x is x ln x minus x. But here we don't want to write the by parts. However, we can easily check. If you derivate the right-hand side, you can get ln x. Now, since we have minus ln x, so it's going to be x minus x ln x. Now, this is the limit of x minus x times ln x from a to 1 when a approaches 0 from positive side. So if I factor from x, let's substitute the upper limit first. If we substitute upper limit, it is 1 minus 1 times ln1. ln1 is 0, so this is 1 minus. The limit, when I substitute a here, it is a times 1 minus ln a when a approaches 0 from positive side. So when a approaches 0 from positive side, ln a approaches minus infinity, and this a to the 0, 0 times infinity is indeterminate form. We need to use Hospital rule. So I can continue by one Hospital rule. Here this ln1 is 0, we have just 1 here minus the limit. So we can write this 1 minus ln a in numerator and take that a to denominator and write 1 over a when a approaches 0 from positive side. Now it is infinity over infinity. We can use Hopital rule. One minus limit derivative of 1, 0, derivative of ln a 1 over a minus 1 over a, derivative of 1 over a minus 1 over a squared. A approaches 0 from positive side. And if we simplify, it is only a, and a approaching 0, this is still 0, so this is convergent. Another improper integral, however, I wanted to show this one as first type. Let's study the same problem as let's use the substitution first. If I use a substitution, like if I take ln x as t, then x is e to the t, dx is e to the t dt. When x is 1, then t is ln1 is 0. When x approaches 0 from positive side, then t, which is ln x, approaches minus infinity. Or if I take minus ln x as t, then it can be positive infinity. It's up to us. So if I select this one as minus, then it can be minus. So let's keep like this. So if I use this substitution, then the new integral is going to be from, at 0 we have minus infinity instead, 1 we have 0, ln x is t, dx is e to the t dt. Now we can study this first type improper integral instead of the second type. And we know that to integrate this, again, we can use the by parts derivative integral minus t e to the t, derivative of minus t, integral of e to the t, derivative integral, and uv minus v du plus and minus. And if I factor from e to the t, this is going to be the limit e to the t multiplied by, here we have 1 minus t, from a to 0 when a approaches minus infinity. And this is the limit. If I substitute upper limit, it is e to the 0 times 1 minus 0 minus the limit e to the t 1 minus t. I write 1 minus t divided by e to the minus t. When, let me write a, so I'm substituting a, 1 minus a, this e to the a in denominator, e to the minus a when a approaches minus infinity. Now if a approaches minus infinity, in numerator we have infinity, and this negative a is positive infinity, so infinity over infinity, again we can use Hopital rule. So here we have infinity over infinity. We can use Hopital rule. So the first time here, e to the 0, 1, 1 times 1. Here we have 1 minus. The limit, Hopital rule for 1 minus a is minus 1. E to the minus a minus e to the minus a approaches minus infinity. So it becomes 1 over plus infinity, which is 0. The same result as we found in the other form. Another example, this time we need to use partial fractions. So instead of this x plus 1, x squared plus 1, let's write the partial fractions first. We know that we are going to have x plus 1, x squared plus 1, a1, a2x, a3. So instead of this, if I write two partial fractions, if we add, the numerator must be equal to 1 here. So I know that a times x squared plus 1 plus a2x plus a3 times x plus 1 is the polynomial 1. First, we substitute the root for this first order polynomial or the degree 1 factor, x plus 1. So if I substitute x by minus 1, this parenthesis becomes 0. This one is 2, so 2a is 1, or this is a1. Then a1 is 1/2. For the other two, a2 and a3, I can consider, for example, the constant part. The constant part for left-hand side, here we have a1 and another a3 here. Right-hand side, the constant part is 1. So we can see that a1 is 1/2 and the sum of a1 and a3 is 1. And it says that a3 also is 1/2. And a2 we can consider, let's say, degree 2. Left-hand side we have a1 x squared. And here we have a2 x squared. Right-hand side we have no x squared, so it is 0 times x, 0 times x squared. So this must be equal to 0. And since a1 is 1/2, then a2 is minus 1/2. Now if we rewrite this, it can be equal to a1 is 1/2, x plus 1 minus 1/2 x plus 1/2 x squared plus 1. Or we can factor from 1/2 and just write 1 over x plus 1 minus x plus 1 over x squared plus 1 and so forth. So we know what's going to be the indefinite integral. Even we can write it and then go for just finding the limit for improper integral. Now if I want to find the indefinite integral, dx x plus 1 x squared plus 1 is 1/2 integral 1 over x plus 1 minus x plus 1. Instead of this minus x plus 1 also I write separately minus x over x squared plus 1 1 over x squared plus 1 dx, which is 1/2 ln x plus 1. Here, derivative of denominator needs only a 2 in numerator, so I need to write minus 1/2 ln denominator x squared plus 1. And the last one is tan inverse x. We can simplify the first term here. Ln a minus ln b is ln a over b. Because we want to find the limit, it's better to simplify. Here we have ln x plus 1 divided by this 1/2 goes to power here, and we have root x squared plus 1. and tan inverse x. Now if we want to find the improper integral, we need to find the limit at infinity of this term. Now this integral is going to be the limit from 0 to b when b approaches infinity of this term, dx x plus 1 x squared plus 1. And we know the indefinite integral here. We can substitute once b and find the limit, another time 0. Now this is equal to the limit of 1/2 ln x plus 1. Since x starts from 0 to infinity, then we don't need the absolute value. And 1/2 tan inverse. Let me write, instead of x, I'm going to write again b. And b approaches infinity. So let me change this x also to b. This is an upper limit minus. At lower limit, we have 0 to be substituted, which is 1/2 ln 1 over root 0 plus 1, root 1, which is ln 1 still 0, plus tan inverse 0, and this one also is 0. So this ln 1 is 0, tan inverse 0 is 0, and the limit at infinity. The limit infinity of this ratio is 1, and ln 1 approaches 0 again, so this limit also approaches 0. And tan inverse when b approaches infinity is pi over 2, so this is 1/2 times pi over 2 or pi over 4. This one also is convergent. Now let's see one divergent in improper integral also. Imagine we have integral one over x from 2 to infinity. So this is first type. Then I need to write limit 2 to b. B approaches infinity. Integral of 1 over x ln x from 2 to b when b approaches infinity. And this is limit of ln b when b approaches infinity, upper limit, minus ln 2. So ln 2 is a constant, but this limit is infinity. So the limit approaches infinity when this limit does not exist or the integral is divergent. So the integral diverges to infinity. This one approaches infinity.